A furnace is a device used for high-temperature heating. The name derives from Greek word fornax, which means oven. In American English and Canadian English usage, the term furnace on its own refers to the household heating systems based on a central furnace, and sometimes as a synonym for kiln, a device used in the production of ceramics. In British English, a furnace is an industrial furnace used for many things, such as the extraction of metal from ore or in oil refineries and other chemical plants, for example as the heat source for fractional distillation columns. The term furnace can also refer to a direct-fired heater, used in boiler applications in chemical industries or for providing heat to chemical reactions for processes like cracking, and is part of the standard English names for many metallurgical furnaces worldwide. The heat energy to fuel a furnace may be supplied directly by fuel combustion, by electricity such as the electric arc furnace, or through induction heating in induction furnaces. Large furnaces. A large furnace is a major appliance that is permanently installed to provide heat to an interior space through intermediary fluid movement, which may be air, steam, or hot water. Heating appliances that use steam or hot water as the fluid are normally referred to as a residential steam boiler or residential hot water boiler. The most common fuel source for modern furnaces in the United States is natural gas. Other common fuel sources include LPG, fuel oil, coal or wood. In some cases electrical resistance heating is used as the source of heat, especially where the cost of electricity is low. Modern high-efficiency furnaces can be 98% efficient and operate without a chimney. The small amount of waste gas and heat are mechanically ventilated through PVC pipes that can be vented through the side or roof of the house. Fuel efficiency in a gas furnace is measured in AFUE. Categories. Residential furnaces can be classified into 4 general categories, based on efficiency and design. Natural draft. The first category would be natural draft, atmospheric burner furnaces. These furnaces consisted of cast iron or riveted steel heat exchangers built within an outer shell of brick, masonry, or steel. The heat exchangers were vented through brick or masonry chimneys. Air circulation depended on large, upwardly pitched pipes constructed of wood or metal. The pipes would channel the warm air into floor or wall vents inside the home. This method of heating worked because warm air rises. The system was simple, had few controls, a single automatic gas valve, and no blower. These furnaces could be made to work with any fuel simply by adapting the burner area. They have been operated with wood, coke, coal, trash, paper, natural gas, and fuel oil. Furnaces that used solid fuels required daily maintenance to remove ash and clinkers that accumulated in the bottom of the burner area. In later years, these furnaces were adapted with electric blowers to aid air distribution and speed moving heat into the home. Gas and oil-fired systems were usually controlled by a thermostat inside the home, while most wood and coal-fired furnaces were controlled by the amount of fuel in the burner and position of the fresh air damper on the burner access door. This style furnace was used to replace the big, natural draft systems, and was sometimes installed on the existing gravity ductwork. The heated air was moved by blowers which were belt-driven and designed for a wide range of speeds. These furnaces were still big and bulky compared to modern furnaces, and had heavy steel exteriors with bolt-on removable panels. Energy efficiency would range anywhere from just over 50% to upward of 65% AFUE. This style furnace still used large, masonry or brick chimneys for flues and was eventually designed to accommodate air conditioning systems. Forced draft. The third category of furnace is the forced draft, mid-efficiency furnace with a steel heat exchanger and multi-speed blower. These furnaces were physically much more compact than the previous styles. They were equipped with combustion air blowers that would pull air through the heat exchanger, which greatly increased fuel efficiency while allowing the heat exchangers to become smaller. These furnaces have multi-speed blowers and were designed to work with central air conditioning systems. Condensing. The fourth category of furnace is the high-efficiency, or condensing furnace. High-efficiency furnaces can achieve from 89% to 98% fuel efficiency. This style of furnace includes a sealed combustion area, combustion draft inducer and a secondary heat exchanger. Because the heat exchanger removes most of the heat from the exhaust gas, it actually condenses water vapor and other chemicals as it operates. The vent pipes are normally installed with PVC pipe versus metal vent pipe to prevent corrosion. The draft inducer allows for the exhaust piping to be routed vertically or horizontally as it exits the structure. The most efficient arrangement for high-efficiency furnaces include PVC piping that brings fresh combustion air from the outside of the home directly to the furnace. Normally the combustion air PVC is routed alongside the exhaust PVC during installation and the pipes exit through a side wall of the home in the same location. High-efficiency furnaces typically deliver a 25% to 35% fuel savings over a 60% AFUE furnace. Heat distribution. The furnace transfers heat to the living space of the building through an intermediary distribution system. If the distribution is through hot water or through steam, then the furnace is more commonly called a boiler. One advantage of a boiler is that the furnace can provide hot water for bathing and washing dishes, rather than requiring a separate water heater. One disadvantage to this type of application is when the boiler breaks down, neither heating nor domestic hot water are available. Air convection heating systems have been in use for over a century, but the older systems relied on a passive air circulation system where the greater density of cooler air caused it to sink into the furnace, and the lesser density of the warmed air caused it to rise in the ductwork. The two forces acting together to drive air circulation in a system termed gravity feed. The layout of the ducts and furnace was optimized for short, large ducts. This caused the furnace to be referred to as an octopus furnace. By comparison, most modern, warm air furnaces typically use a fan to circulate air to the rooms of house and pull cooler air back to the furnace for reheating. This is called forced air heat. Because the fan easily overcomes the resistance of the ductwork, the arrangement of ducts can be far more flexible than the octopus of old. In American practice, separate ducts collect cool air to be returned to the furnace. At the furnace, cool air passes into the furnace, usually through an air filter, through the blower, then through the heat exchanger of the furnace, whence it is blown throughout the building. One major advantage of this type of system is that it also enables easy installation of central air conditioning. Simply by adding a cooling coil at the outlet of the furnace, air is circulated through ductwork, which may be made of sheet metal or plastic, flex duct, and is insulated or uninsulated. Unless the ducts and plenum have been sealed using mastic or foil duct tape, the ductwork is likely to have a high leakage of conditioned air, possibly into unconditioned spaces. Another cause of wasted energy is the installation of ductwork in unheated areas, such as attics and crawl spaces, or ductwork of air conditioning systems in attics in warm climates. Furnace types. Single stage. A single-stage furnace has only one stage of operation. It is either on or off. This means that it is relatively noisy, always running at the highest speed, and always pumping out the hottest air at the highest velocity. One of the benefits to a single-stage furnace is typically the cost for installation. Single-stage furnaces are relatively inexpensive since the technology is rather simple. Two-stage. This type has two stages of operation, full speed and half speed. Depending on the demanded heat, they can run at a lower speed most of the time. They can be quieter, move the air at less velocity, and will better keep the desired temperature in the house. Modulating. This type of furnace can modulate the heat output and air velocity nearly continuously, depending on the demanded heat and outside temperature. This means that it only works as much as necessary and therefore saves energy. Possible failures. The following rare but difficult to diagnose failure can occur. If the temperature inside the furnace exceeds a maximum threshold, a safety mechanism with a thermostat will shut the furnace down. A symptom of this failure is that the furnace repeatedly shuts down before the house reaches the desired temperature. This is commonly referred to as the furnace riding the high limit switch. This condition commonly occurs if the temperature setting of the high-limit thermostat is set too close to the normal operating temperature of the furnace. Another situation may occur if a humidifier is incorrectly installed on the furnace and the duct which directs a portion of the humidified air back into the furnace is too large. The solution is to reduce the diameter of the crossfeed tube, or install a baffle that reduces the volume of refed air. Metallurgical furnaces. In metallurgy, several specialized furnaces are used. These include furnaces used in smelters, including the blast furnace, used to reduce iron ore to pig iron, steelmaking furnaces, including puddling furnace, reverberatory furnace, Bessemer converter, open hearth furnace, basic oxygen furnace, electric arc furnace, electric induction furnace, reheating furnace. Furnaces used to remelt metal in foundries. Furnaces used to reheat and heat-treat metal for use in rolling mills, including tin plate works and slitting mills. Forges. Vacuum furnaces.